Now we're going to look at our longer answer questions. Here we're asked to consider this function and to show that it's a continuous function. To show that it's a continuous function, we want to use the direct substitution property. Okay? That is something we would love to use. So to use the direct substitution property, what we're going to do is we are going to notice that there's no domain constraints. There are no domain constraints. Thus, by the direct substitution property, we are continuous everywhere. What you'll notice in these long answer part B questions is the argument we use will show up more and more in these questions. The rapid fire questions, it was if you know the theory, what's the answer? Now we care more about the argument. In part B, we want to show that the limit as x approaches infinity equals infinity, while the limit as x approaches infinity of e to the x minus e to the minus x all over 2 equals infinity minus 0 over 2, which equals infinity over 2, which equals infinity. And I have shown that the limit goes to infinity. Now, this is how we're computing the limits. Okay. Now, there was another question that I had that I think I removed. And it was show that the limit as x goes to minus infinity of sinh of x equals minus infinity. And this here, if we have the limit as x goes to minus infinity of e to the x minus e to the minus x over 2, this equals e to the minus infinity minus e to the infinity over 2, which equals 0 minus infinity over 2, which equals minus infinity. In part C, we want to show that the inverse function of ln of x plus the root of, or the inverse function of the inverse of the sinh function, arcsinh, is ln of x plus root x squared plus 1. To do this, we start with y equals e to the x minus e to the minus x over 2. And you'll notice here, I required you to know what the sinh function is, and also know what the cosh function is. I haven't explicitly given you the cosh function, but because I expected you to know what the sinh function is, it's reasonable to think I'll also expect you to know what the cosh function is. Then what we're going to do is we're going to swap our x's and our y's. So x equals e to the y minus e to the minus y over 2, or 2x equals e to the y minus e to the minus y. And I'm going to multiply both sides by e to the y. Okay? And this gives me 2x e to the y equals e to the y, e to the 2y minus 1. I'm now going to bring this over, giving me 0 equals e to the 2y minus, well, I guess here these should be e to the y squared. So it's e to the y squared minus 2x e to the y minus 1. Now, e to the 2y is the same as e to the y squared. But now what we have, if we let this be a, if e to the y equals a, then we have a squared minus 2xa minus 1, which is a quadratic. So we can solve it using the quadratic formula. So this implies that e to the y equals 2x plus or minus the root of 2x minus 2x all squared minus 4 times 1 times minus 1 all over 2, which implies that e to the y equals 2x plus or minus, and we get the square root of 4x minus 4 all over 2, which implies that e to the y equals 2x over 2 plus or minus the root of 4 times x squared minus 1 all over 2, which equals x plus or minus 2 root x squared minus 1 over 2, which equals x plus or minus the root x squared minus 1. Or x squared plus 1. And now, as e to the y is always positive, as e to the y is greater than 0, we take the positive case. So e to the y equals x plus root x squared plus 1. And now I take the ln of both sides. Give me y equals ln of x plus root x squared plus 1. And I have my result. Nice. This gives us our solution. Question 8. I need to compute my natural domain, and where I have a discontinuity, I need to classify the discontinuity. So B2 is another question. I realized that I made a mistake with the ln, so we're going to redo it. So to determine the natural domain, we break it up into 3 pieces. 1, 2, and 3. We have x less than 1. Here I have ln of x, which implies that x is greater than 0. So with x being greater than 0 and x being less than 1, the domain piece for this portion is x is in the interval 0 to 1. For x equaling 0, f of x equals 0. So I get the single point, or sorry, for x equaling 1, f of x equals 0. So we have the single point 1. And for x greater than 0, I have the absolute of x minus 2 over x minus 2 minus 1. And here, the 1 over x minus 2 implies that x cannot equal 2. So I get the interval 1. Again, this should be a 1 here, x greater than 1. 1 onward, combined with the interval everywhere except 2, to give me the interval 1 to 2, not including 2, union with 2 to infinity. To get my overall domain, I take the union of these sets. I get 0 to 1, 1, and 1 to 2 up to infinity. Unioning these, 0, I include 1, I don't include 2 to infinity, or my domain is the set 0 to 2 union with 2 to infinity. And now I have to deal with my types of discontinuities. So for discontinuities, we have 3 main spots. We have the stuff from ln, we have the jump at 1, and we have the stuff from this absolute x minus 2 over 2 minus x minus 1. First thing we have is from the ln. Ln of x implies that for all x less than or equal to 0, the limit as x approaches 0 from the negative of f of x equals the limit as x approaches 0 from the negative ln of x, which does not exist. Thus, x less than or equal to 0, if x is less than or equal to 0, then x is an essential discontinuity. Okay. Then we have at 1. Okay. I'm going to try and I'm going to do at 1 up here, just so that we have some more space. And for at 1, the limit as x approaches 1 from the negative of f of x equals the limit as x approaches 1 from the negative of ln of x, which equals ln of 1, which equals 0. The limit as x approaches 1 from the positive of f of x equals the limit as x approaches 1 from the positive of absolute x minus 2 over x minus 2 minus 1, which equals 1 minus 2 over 1 minus 2 with an absolute on top, minus 1, which equals absolute of minus 1 over minus 1, minus 1, or 1 over minus 1, minus 1, which equals minus 2. As the limit as x approaches 1 from the negative of f of x equals 0, which is not equal minus 2, which equals the limit as x approaches 1 from the positive of f of x. The limit as x approaches 1 of f of x does not exist. Thus, we have a jump discontinuity at x equals 1. Now, at x equals 2, f of x is not defined. So we are not continuous at x equals minus 2. And this turns out to be a jump discontinuity as well, because my 2 directional limits are not equal. But I'm going to leave that as an exercise for you to show to yourself that you have a jump discontinuity there.